Hi, everyone. Welcome to Foresight's Intelligent Cooperation Group. This is a special kind of type of series where we really focus a lot on cryptography and the intersection of cryptography and machine learning and the intersection of really cryptography and privacy-preserving technologies in particular, and the kind of promises that they have for different cooperative structures across humans and ultimately perhaps also AIs. And in order to perhaps like just lay the land a little bit, this is our first meeting of this year, so I'm really excited. This year is now, I think, this group is now in its third year. So thanks all for those of you who have been here for a really long ride already. I do want to make you aware of like one event that we have in person. So many of you have already been there last year, but we do have our cryptography security AI workshop, which is really looking a little bit more at the decentralized path between a human and AI cooperation enabled by cryptographic technologies. So if you're interested in that, that's going to happen in the Bay Area in July. And we have a bunch of really exciting seminars coming up, and they are all found on our computing seminar group. I'm going to share them here in the chat already, but we're going to have Divya as well coming on. We're going to have Stuart Russell on next. And today we have the wonderful Natalie Dullerud from Stanford. And so at least physically relatively close to me right now. And we're really, really happy to have you here and really excited about the work that you're doing. And so from now on, the stage is yours. You're going to be presenting on confidential, private, collaborative learning. So top topic for this group. And I'm going to share more info about you here in the chat. I'll be in the chat. And if you have any questions, feel free to already ask them in the chat or raise your hand afterwards and we'll get to them when we get to them. But thanks a lot for coming. It's a real pleasure to have you.
Yeah, thank you so much for having me. And I'll go ahead and share my slides. And then we can, kick off the presentation. So thanks so much, obviously, for introducing me, Allison, and thanks to everyone here for attending the presentation. As Allison said, my name is Natalie Dullerud, and I'm a current PhD student at Stanford. And today I'm going to be talking about a project I did during my master's at University of Toronto in Dr. Nicholas Paperno's lab. And this was published at a machine learning conference last year, Confidential and Private Collaborative Learning, which was a group effort with my awesome colleagues who are listed here. So I'll be giving kind of a brief overview of federated distributed learning, sort of the privacy issues that arise in this setting, and then our proposed solution and sort of future work in securing distributed learning. And I know many here are probably familiar sort of with some of these sort of topics and the current state. So I'll try to sort of focus a bit more on technical details and the specific solution that I've worked on later on in the presentation. Let's go ahead and start with sort of conceptualizations of distributed and federated learning. Though, as I said, many in the audience are probably familiar with at least some sort of background on distributed learning. And throughout the talk, I'll use sort of distributed, collaborative, and federated learning interchangeably. Though, in terms of the real usage of these terms, there are sort of some minor differences. So in distributed learning, sort of the high level idea is that we have sort of a set of parties or devices. Each of them have their own data and they interact in order to train a model on their collective data. And sort of there are differing methods for how the interaction between these parties can occur. I'll quickly walk through the centralized framework and I'll sort of describe some alterations such as decentralized learning and heterogeneous learning. And so in the centralized distributed learning setting, there's a single model that the parties learn. And the model is generally held on a sort of central trusted server. And each party here or device sort of involved in the learning process usually retains their own data set. Which is not shared amongst devices nor with the central server. So assuming that we're using stochastic gradient descent or some similar algorithm to update the model, a copy of the global model is sent to each party's device, which then computes the gradients with respect to the global model parameters on locally stored data. And then these gradients are returned to the central server, which aggregates these gradients across devices, typically via averaging, and updates the model via gradient descent. And as with sort of traditional machine learning methods, this is generally an iterative process. It continues for some number of epochs. So that's sort of the centralized learning setup. And decentralized learning, instead of sort of a central server mitigating and training between devices, usually the parties or devices themselves are able to coordinate to train a global model. And now there's kind of been an increasing surge in interest in a concept called heterogeneous distributed learning. And one can sort of imagine that many application domains involve, a large set of heterogeneous devices or heterogeneous parties who might wish to sort of train their own local models that have sort of unique model architectures, but they still want to benefit from access to data from other devices without having to copy that data onto their own device. So this is sort of a nascent field and one that's sort of difficult to resolve in this federated learning setup. And we'll kind of return to that later. So now that I've introduced sort of some background on federated learning, I'll talk a bit about why federated learning is more and more considered sort of the new horizon in AI. And so obviously in traditional machine learning, resource costs and efficiency are sort of a significant issue. So to train a very high performing deep neural network model, you need to have sufficient data, sufficient storage ability, unrestricted GPU access for up to, orders of days. But with federated learning, we outsource steps of SGD, stochastic gradient descent, to, potentially millions of parties, which each have sort of their own data sieve to draw from. So on a device level, we save pretty big time on computation. And this setup enables, continual learning on end user or party devices, while ensuring that sort of the end user data doesn't actually leave the device. And so related to that point, while we sort of constantly discuss living in the age of big data, data is sort of commonly spread out between devices. So for example, in smartphones, every smartphone user has tons of text prediction information from all the apps that have, user input text, and which is stored on their device. But if we think about it on sort of an institutional level, banks and hospitals, other sort of institutions often have really huge sieves of data stored locally and protected. And federated learning allows the server to sort of save on storage by only requiring aggregation of model updates, but you don't have to actually store the aggregated data from all the participating devices. Um, and sort of one of the final sort of important parts of why sort of federated learning has become so big is natural language processing models like BERT are sort of increasing drastically in size, dominantly used, and it's sort of expanding in their use cases. But NLP models generally require sort of enormous sieves of text data that can kind of be difficult to accrue and store in sort of a central location, and they often require many GPUs to train. And so for that reason, sort of the distributed computational and storage burden presented by sort of federated learning is sort of ideal for NLP. Okay, and so now we can move on to sort of understanding where privacy issues generally arise in standard federated learning. And so sort of naturally, we want to motivate why securing federated learning is an important problem, because intuitively, since data is stored sort of on each device separately, there's no data passed between devices. And theoretically, in sort of a colloquial meaning, this means there's no privacy violations, right? So someone intuitively would say that seems like there wouldn't be any sort of data privacy issues. And sort of this is a common stated advantage of federated learning, but the truth is that, even if you don't have explicit data set information exchanged, like directly between the server and the devices, nor between the devices themselves, that, privacy concerns still very much exist. And so even though the devices aren't explicitly sharing data with any other party, the training computations are computed on the data. And for that reason, information could be leaked via this mechanism. And this is a pretty important point. So privacy as a concept isn't really a study of whether an attacker can gain all information about private data, but it's more about whether an attacker can gain any additional information. And whenever you have any sort of information relating to private data shared, we need to sort of carefully examine what an attacker could reasonably learn. And so in the distributed setting, researchers have sort of found that there are sort of multitudinous attack surfaces that need to be addressed in federated learning. And I'll walk through sort of the broad categories of attacks that have been identified, and then we can talk about some of the proposed tools to use as defenses. So sort of in the past few slides, I've sort of predominantly introduced the privacy concern of data leakage. And with data leakage, we're talking about, potentially membership inference, plain text access to sort of private data. And in this case, plain text means non-encrypted data. And so in this sort of simplified example that we have, consider that we have, the two parties colored here. And by some mechanism, the red party gains some sort of unauthorized access to the green party's data, where the sort of access they gain is unencrypted. So alternatively, in inference attacks, we're concerned that based on the gradients returned by the green party to the central server or sent to the red party in a decentralized setup, the red party could infer members of the green party data. And there's kind of only been limited exploration of this attack and kind of in a constrained context. But nonetheless, sort of the idea with this attack is that because data points in the Green Party's data have been used to train the model will have very good performance on the Green Party's data. And for that reason, the gradients will likely be very small on the Green Party's data. And so then the red party, based on sort of the gradients with respect to different data points, could potentially figure out which data points were in the green party's training data. And so ultimately, data leakage results in the red party discovering the private data points stored as part of the green party's data. So moving on to model leakage is kind of a concern in the heterogeneous setting that I mentioned earlier, where each party trains their own model architecture separately, but leverages federated learning to sort of boost the accuracy of their model. And in many cases, model architectures could sort of be considered intellectual property. So if the red party is able to discover the model architecture designed by the green party, the red party could then publicly claim ownership of a model that they didn't design. And a sort of a distinct idea of a privacy concern, in addition to sort of model leakage and data leakage, which is kind of more intuitive to us, someone stealing something else, a distinct idea is sort of corrupted computation. And this doesn't really involve any information leaking, but let's say a device is adversarial and wants the training process to result in a model with poor performance. Then the device could simply return updates to the model that are, completely random or corrupted or potentially adversarial in the sense that they explicitly hinder sort of the model performance. So instead of computing a valid gradient descent update sort of on data, they simply return some sort of random information. And that random information then is used to update the model. And it's likely that, this will degrade the model. So intuitively, this will be less of an issue if we have, hundreds or millions of devices. But if many of the devices are compromised or corrupted, we may end up with a very poor model. And so finally, often in the centralized setting or when there's a central sort of execution or communication channel, we sort of make the assumption that the server is trusted, but there are side channel attacks that are possible on the central server, and attackers might be able to gain information from the central server that isn't authorized. Okay, so what tools can we use to sort of address these issues and secure distributed learning? So based on sort of the attack surfaces I previously discussed, we can use, for instance, differential privacy. And differential privacy generally used to sort of protect against the inference attacks that I mentioned earlier. Sort of, I won't go into like super extensive detail on the theoretical formulation, but essentially differential privacy in deep learning generally boils down to adding noise to the gradient updates passed between devices and the central server to try to obfuscate any sort of retrievable information about the individuals in the private training data set held by each party. So then an adversarial party or device can't use gradients to determine whether a data point was contained in the private data of another party. But obviously adding noise to gradients will cause some degradation in model utility. So we can also draw on cryptography for our remaining tools. So computation over encrypted data and using trusted execution environments, also called TEEs, for the central server could restrict sort of plain text access to data or gradients. However, nonetheless, TEEs are still vulnerable to side channel attacks. And so, there are still some drawbacks with sort of both of the methods that I've mentioned so far. And so finally, we have verifiable computation, where an auditor engages in some interactive process with the device to ensure that the training computation was computed correctly. And then this can be used to verify that, the return training computations were done correctly so that, adversarial devices can't potentially return corrupt updates to the model. And this approach to corrupted devices is still sort of in its infancy in machine learning. But if federated learning is sort of deployed large scale, this is sort of an important piece of securing federated learning. And so currently there are many state-of-the-art approaches that involve these tools to defend against, various attacks that we have discussed. And in many cases, these are predominantly research-based tools that haven't really been deployed yet. And there are still, several drawbacks that sort of could affect realistic deployment. So in sort of standard federated learning, we also have some disadvantages that we sort of need to overcome in order to sort of further the applicability of federated learning. So generally, the standard setup is sort of inflexible. As I mentioned sort of earlier in the talk, heterogeneous sort of federated learning has sort of large scale applicability, but it's difficult to achieve in sort of a cost effective way in standard federated learning. And combined with restricted communication abilities in centralized and decentralized frameworks, this leads to sort of some inflexibility. And so the second part is that standard federated learning typically requires sort of millions of devices or parties in order to achieve sort of the improvement over traditional machine learning. And access to millions of parties is quite realistic in some settings. If the parties are smartphones or something like that. But if the parties are institutional, like hospitals, that's not necessarily a realistic setting. Maybe a handful of hospitals will be collaborating. And so obviously standard federated learning also doesn't sort of provide any level of privacy. And so while privacy preserving methods that I introduced in the last slide sort of address this last point, privacy preserving federated learning tends to have weighty sort of privacy utility trade-offs where increasing privacy leads to, potentially worse model utility or very high computation time. And that ultimately sort of negates the purpose of collective model training. And a similar thing can sort of be said for computational overhead introduced by privacy measures, which hinders sort of a purported advantage of federated learning, which is efficiency. And additionally, we have sort of the issue that there isn't an elegant solution to addressing all of the privacy concerns that we have. So most approaches to private federated learning sort of only address one of the attack surfaces that we discussed. And sort of at best, what we have right now is sort of just layering these sort of defenses on top of each other, which often really isn't that elegant sort of a solution. Okay, so then what should we sort of require of an improved method that addresses some of these drawbacks? So we primarily want to address both the setbacks in standard federated learning that sort of limit applicability, and we want to sort of also multiply sort of private learning that we want to kind of have private learning that doesn't introduce sort of significant computational or accuracy trade-offs for training the model. And so this sort of leads me to introducing our recent work, confidential and private collaborative learning, or CaPC, which satisfies sort of these requirements that I laid out. So sort of first, how does it satisfy these? So we propose sort of a hybrid setup where the devices can communicate between themselves. So we have some decentralization and sort of facilitation of heterogeneous model architectures, but we additionally have a central party, which we call the sort of content service provider, or CSP, that manages certain private computations. And we also require fewer parties in order to see a boost in model accuracy by allowing sort of querying between the parties in a privacy preserving manner that allows parties to learn from each other's separate models. In addition to that, we protect against attacks on the central party or sort of a curious central party by only allowing data to pass through the CSP that is encrypted and cannot be read in plain text by the content service provider. So finally, sort of in order to address multiple attack surfaces, we combine encryption and differential privacy. And finally, with our querying approach between parties, we introduce a collaborative learning paradigm that enables boost in accuracy. So we'll quickly dive into how the learning paradigm works here. And this CaPC framework is largely based on PATE, which is kind of a rather well-known differential privacy algorithm with some sort of significant adaptations. So our framework sort of contains two training stages. So recall that we have this sort of hybrid decentralized setup that also has a central party, the CSP. So we assume that each party has access to at least a small sieve of labeled data and potentially a very large sieve of unlabeled data. And this is, a very realistic assumption as, data itself is sort of cheap, but labeled data is very expensive. But it's necessary to sort of train a supervised machine learning model. So first what we have is each device separately trains their model on their own local labeled data. And then in the second stage, we have the collaborative part. So in this part, devices can communicate amongst themselves and use their unlabeled data to query all or a portion of the other parties in order to obtain a label for all of their unlabeled data points. So essentially, they're sort of leveraging the response of the parties in the sort of collaboration to label their unlabeled data. And then they can use that to continue to train their local model. So this sort of exchange between parties is completed in a private manner with encryption and differential privacy so that we can query other models without privacy concerns. So here I have sort of a short infographic that describes the second stage of CaPC. So imagine here that our querying party on the right here is a hospital, and they've trained a model to, for example, determine the diagnosis of a patient based on the patient's data. And now sort of a new patient comes in and needs to be diagnosed. And this patient is sort of unlabeled from the ML model's perspective. And so for that reason, we can hopefully use CaPC to obtain a label for the patient and update the hospital's model. And so to do this, the querying party hospital encrypts their unlabeled patient data, sends their queries to the other parties in this setup, which in our case would likely be partnering hospitals, which we've named answering parties here. And the answering parties then feed this encrypted data through their model via a method called private inference. And their encrypted model predictions are aggregated via differential privacy by the central party to come up with noisy votes for different predictions of diagnoses. So in this case, we see that hernia has the highest votes amongst the other parties' predictions. So the CSP will return the hernia label to the querying party, and the querying party will use that to label their patient and continue to train their model. And so here, essentially the sort of green part of hernia and the red part of appendicitis is sort of the true votes by the answering parties. And then this sort of dotted line around the top part is the noise that would be added to those votes. So we can see that, hopefully in cases where most of the answering parties agree with each other, we still get the correct diagnosis. It doesn't affect the ultimate outcome too much, but we are still retaining privacy. And in some cases, the outcome might be changed. So here's sort of a more technical diagram that describes the steps of CaPC for achieving encryption and differential privacy. And so the content service provider here is the central party who adds noise to the encrypted answering party votes. So we can sort of go through each part of the approach here. So first, sort of any party can initiate the protocol as the querying party. And in step 1A, the querying party will send their encrypted data to all the answering parties. And then the answering parties will use private inference to get the model logics, which are the unnormalized model predictions for each class on the encrypted data. And in our current implementation, we use combination of homomorphic encryption and multi-party computation in order to achieve private inference over a neural network. But theoretically, this framework should work for any private inference method. And then in step 1B, to prevent differential privacy leakage, each answering party will secret share their logics with the querying party by subtracting a random vector R from them before sending. So this acts as a form of encryption, preventing the querying party from gaining plain text access to the logics before the sort of pate component of this sort of setup is performed. So in step 1C, the querying party and each answering party will engage in a two-party computation protocol, which computes the one-hot encoding of the logits. So this is a binary vector with one only at the index of the predicted class. And the querying party and the answering party each receive one share of the one-hot encoding. So that summing the two shares reveals the true one-hot encoding, but each of them gets one share of it. And so this sort of prevents either party from viewing this vector, this sort of binary encoding of the logits in plain text. And then in step 2, each answering party sends its share to the content service provider, who will sum the shares and add noise to achieve the differential privacy guarantees of pate. And then at the same time, the querying party has a share from each of the answering parties, and they will sum their shares. And finally, in step 3, the content service provider and the querying party engage in a two-party secure computation protocol to sum each of their sum shares, which then removes the secret sharing to reveal the plain text but noised value. And so the result is the differentially private final label. Okay, so based on this, what exactly is CaPC protecting against? So CaPC prevents data leakage via inference attacks by the CSP adding noise to the sum shares of the answering party. It also prevents data leakage in the sense of plain text leakage, as all the computations are done over encrypted data. And similarly, because all model computations are computed over encrypted data, the model weights and the architecture of all of the answering parties are protected. And then finally, since the central party only sees encrypted sum shares from the answering parties, we don't have any plain text privacy leakage to the central party. Okay, so as I said earlier, a sort of significant advantage of CaPC is the improvement in performance seen by querying parties to their model by labeling their unlabeled data via private voting by the answering parties. And we see this boost in performance across model architectures, both homogeneous and heterogeneous, and across data sets. And additionally, we have sort of the flexibility of having very few parties compared to sort of traditional federated learning. So our results are obtained on collaborative learning between fewer than 200 parties. So here we see sort of the accuracies of the querying parties' local models prior to engaging in CaPC. So between the first and the second phase of training in blue, and after engaging in CaPC, or after the second phase of training in yellow. And these are shown for each class label in the displayed data sets and for both homogeneous and heterogeneous model architectures across the parties. And here we can see sort of across the board, we have an increase of up to 5% in accuracy. But this sort of boost in performance becomes twice as large when we experiment in data skew domains, which are much more realistic. So the sort of data skew or class imbalance settings arise when each party has data that is drawn from a differing data distribution. So for example, we might imagine in a hospital setting that geographic location or urban versus rural will sort of heavily influence which diagnoses are seen more in certain hospitals. And we are running experiments here in the setting in which answering parties have varying or differing data distribution than the querying parties, and find that when querying is combined with active learning techniques, we see increases in performance of up to 10%, which is a very significant boost. So sort of as demonstrated, the sort of primary advantages of CaPC are the flexible collaborative paradigm that permits both decentralized and centralized learning to occur, in addition to easy heterogeneous learning, and significantly fewer parties are required. to see an improvement in accuracy over standard distributed learning. And so CaPC is also fully private, according to sort of both cryptographic or confidential and differentially private definitions of privacy, with very low reliance on the trustworthiness of the central party. So, as shown in sort of the last slide, we have significant improvements in utility, especially for non-identically distributed data. Um, However, as always, there are sort of areas for improvement. Currently, for the private inference portion of our protocol, we are using sort of out of the box private inference methods, which introduce pretty significant time overhead. And additionally, we still sort of require on the order of tens of parties in order to see an improvement in model accuracy. But we want to be able to do better. So say, for example, a handful of parties can choose to collaborate, maybe less than 10, and they can still see a boost in performance from this collaboration. Um, and so, still sort of building off of these areas for improvement, what does sort of the future look like in terms of securing distributed learning and readying privacy preserving distributed learning methods for deployment? And so, in terms of sort of realistic deployment scenarios, we consider sort of largely domains in which we require both sort of stringent security constraints and excellent utility. And as we saw with CaPC, it works very well in the non-identically distributed data scenarios. And where do we generally find these? So, sort of the primary deployment domains we would consider are sort of high-risk domains like healthcare or finance. But we would also want to consider CaPC between companies that sort of generally focus on sort of personalized ads or recommender systems. Um, and so, to sort of further aid in deployment scenarios for securing distributed learning, there are sort of more domain specific issues that we need to address. So, one of them is vertically partitioned data. So, right now we're looking at horizontally partitioned data. And there has been sort of some work done on vertical partitioning of data in the federated learning setting. Essentially, horizontal partitioning amounts to you have full feature sort of observability, or you have a full range of features for each data point that you have in sort of each party that you have, but the data points between parties are different. The vertically partitioned scenario, you might have, for example, many of the parties have the same data points, so they have data on the same individuals, but their features are shared sort of unequally between parties. So you can think about, for example, maybe in the hospital setting, a patient has gone to several different hospitals. Each of those hospitals maybe has different, X-rays, diagnoses, labs on this one patient, and that sort of those features are spread across the different hospitals. It's not all contained in one hospital, so that would kind of be the sort of vertically partitioned data setting. In addition, we want to maybe address, different target distributions. So here we're talking about, one sort of institution might have different classes or different sort of targets that they're interested in sort of looking for in terms of labels. And we want to be able to at least somewhat support that through sort of supporting some sort of union or intersection of labels between the parties, such that we can still sort of leverage this. And then we also sort of want something with sort of to focus on more sort of domain specific attacks. And so this, can be kind of a range of things, but basically looking at, for example, in the finance sector, what sort of very specific attacks, what might we want to protect against? And so the sort of example for one of those is like the current methods for sort of CaPC, and this relates to sort of the other threats that we're worried about, is we have this central party. And as I said earlier, we protect against, if the central party is, curious, it could look at the data, but it wouldn't be able to learn anything about the data. But we do rely on the central party being honest in the sense that it will properly sum the shares that it's given and also properly add the noise, which doesn't necessarily protect against sort of delegated computation corruption. So if the central party is, say, dishonest, it could return just completely some random noise instead of the sum shares with the differential privacy noise, which would lead to the querying party getting a completely bogus label. And so this is sort of one thing that we would really like to address. There isn't really any method at the moment that I know of that deals with corruption of computation, data leakage, and model leakage in federated learning all at once. And so just to note, sort of the attack surfaces are sort of very different, but might be necessary for sort of fully securing AI in federated learning scenarios. And hopefully we could come up with something, that's better than just layering these sort of these defenses on top of each other, as that would probably introduce a lot of computational overhead. Um, and so basically, we are kind of already probably seeing a lot of these sort of delegated computation corruption attacks today, but we don't really know how to catch them or how to verify them. And at least at the moment, because FL is mostly deployed in the scenario where we have, potentially millions of devices, you would have to control, like a corrupted party would have to control a lot of those devices in order to have a significant effect on, for example, the model. And so, we don't there's not sort of a pressing need sort of with the current deployed FL models, but I think in the future and to sort of make FL work, we really do need to look at sort of how to verify sort of computations. And then, yeah, some other sort of things that we might want to look at are sort of improving the computational and sort of time incurred by sort of private inference methods. And so, as I said earlier, in CaPC, we look at homomorphic encryption combined with multi-party computation for the purpose of private inference. But this incurs really significant overhead, and also the tool that we use that's implemented already is very is not very robust right now. And so potentially sort of expanding these, making sort of private inference methods more deployable would be sort of another thing that we would want to sort of look at. Okay, so I think I'm a little over, but thank you so much for listening, and happy to sort of start the discussion and talk about questions and stuff.
Awesome. Thank you so much. This was wild. Really, really happy to see so much progress there. I'm immediately going to jump into questions. I think Ami already has one, so maybe Ami, you start, and then maybe I'll get to a few more general questions in the end. But this was really wonderful. Thank you.
Thank you so much, Natalie. This is, yes, in terms of platform view, and I put a question there, which is probably more general, but in terms of platform deployment, how do you see platform being created where there is a continuous usage of CaPC, right, in the industry or in different organizations? For instance, medical research. If people want to work on similar drug discovery and they use each other's models, there's going to be concerns about, of course, derivative work and usage of some data for discovery that may not benefit the first data owners, which would want to put it aside because it's a different conversation. But how easy do you feel it could be to deploy such models where for very fluid, right, collaboration where parties can jump in and jump out, and that relates to permanence or long-term need of access to data, and in your experience?
Yeah. So I think the sort of collaboration is quite sort of flexible in CaPC. So the answering parties, all they sort of require at the beginning is simply that they've trained a model on their data. And the rest of it, sort of setting up the sort of encryption and differential privacy, could, hopefully and theoretically be done without much overhead. So if you wanted to join and then leave, that wouldn't be too difficult. Really, the main part that would sort of affect is potentially the differential privacy accounting. So how many parties are involved in the collaboration matters for how much noise you would end up adding. And so, in sort of loose settings, it would still be okay if sort of someone jumped out. But if you think about, if let's say we first had, tons of parties involved, like I said, we would need on the order of tens of parties in order for sort of the CaPC to see an improvement. If, let's say, the number of parties drop down to below 10, then on sort of queries where the answering parties is, let's say, 6 answering parties, that's still okay. CaPC will still work. It's just that you might see kind of less sort of improvement. But it still should work where, anyone can join at any time as long as they have a sort of model trained on their own data. They can still respond to the sort of querying party, or they can choose not to respond. So I hope that answered the question. I'm not sure.
It does to some extent. Yeah,
Mhm.
my thinking is about the real collaboration at scale.
Mhm.
Basically, platforms we created with CaPC, so there is a fluid accounting of usage and cross training.
Yeah, I think so. As long as your, I guess, model can be sort of easily uploaded onto, for example, like a platform. And I'm not sort of as familiar with sort of the like current sort of deployed software. But as long as your sort of model can be uploaded to the software, then you can, decide, for example, if you receive a query, you can decide whether or not you want your model to sort of run that data through and then respond in the sort of differentially private and encrypted manner. But as I said, sort of the accounting for the privacy would be sort of the main thing. So differential privacy sort of depends on how many parties are answering, and so I think that would sort of be the main sort of bottleneck in terms of like the central party maybe would always need to know how many parties are sort of participating in order to properly adjust the noise that they're adding to their shares, if that makes sense.
Yeah, thank you. That's helpful.
Yeah.
All right, Micah, and then we have Morgan. Cool.
You mentioned a few times that for the corrupted computation issue, if you've got like, let's say, 1 million devices all connected, you have to control a pretty large share. It seems to me that generating legitimate data is very expensive, whereas generating bad data is very cheap. And so it feels like
Yeah.
a single party with a reasonable amount of processing power could easily overwhelm a network with corrupted data because it's so cheap to generate.
That could be true. So I guess the thing is that it kind of depends on the setting. So if each step requires all of the devices to respond, then like one corrupted party can only respond at each sort of at each step. And they only respond with, let's say, one gradient update that's then averaged over the millions of devices. So like let's say they generate some random noise or something that they return to the sort of central party, and then that central party averages that random noise with millions of other legitimate gradient updates. I guess in that scenario it seems like that might be not that big of a deal, but as you said, maybe if, for example, the sort of iterations of SGD are just like each device responds when they can, then what would happen is kind of maybe what you said, is that one device would potentially generate, like, let's say, millions of data points that are just completely bogus and return them to central party, and they keep updating the model based on that. So in that scenario, I could see that happening. I think one thing is that a lot of times, in order to do pretty significant damage to a model in both scenarios, you have to actually generate data adversarially, which is potentially as expensive as generating real data. I hope that answers the question. I could see, though, in the scenario where like every device just responds when they can, like one device can respond like millions of times, for example, just like once, with just tons of corrupted data points, then I could see how what you're describing could happen. Yeah.
Gotcha. And so is the idea then that you would do some sort of simple resistance to ensure that each device is somehow attached to a unique human, and so one person can't just pretend to be 10 million devices?
So I guess in the case, yeah. So I guess like the verified computation setting is essentially you have to provide some sort of if you're sort of familiar with like proof of work type things, you have to provide some sort of proof for the fact that you actually computed a gradient. Um, so you didn't just sort of generate it. So you actually fed data through a model, and then you actually computed a gradient. And like I said, sort of at some point in the sort of talk, like that field of sort of verified computation is like very, very nascent. Like it's not very developed yet. So there's been some very, very limited work in this area on how to verify that someone has done gradient descent, for example. In fact, Nicholas's lab has a couple of recent papers called proof of learning, which is just proving that you computed a set of gradient step iterations, that you actually did do the computation. And so there has been some work done on it, but as I said, it's kind of limited right now.
I think you answered this question. Thank you so much. Next one up, we have Morgan, and Morgan is a Faucet Fellow this year, so really, really happy to have you here. I met Morgan at a DC event a while back, and I had heard a lot about her work before when she was still in the Bay Area. So really, really happy you're joining us, and you focus on cybersecurity and really AI policy, and maybe also are going into more cryptography related work. So thanks a lot for joining.
Thank you, Allison. And yeah, thank you, Natalie, for this talk. This is wonderful. I'm really curious because you talked a bit about the privacy budgeting aspect. And I mean, a huge user design challenge of DP is often exactly privacy accounting.
Yeah.
So like the designing graceful and appropriate noise addition, taking into account like number of users, info, et cetera. And this has been an issue where an area where there have been public failures, like Australian census, things like that.
Yeah.
I'm kind of curious because I was looking into kind of your diagram of it, and I was wondering, one, if you could kind of just go into a little bit what the potential failure modes might be if you don't do the privacy accounting correctly. So kind of where in the process it would fail. And then two, say if I were an external auditor coming in and trying to understand what amount of privacy was or wasn't being added, where could I look into this process and kind of see that?
Yeah, so I think to answer your second question first, because I think that's slightly easier to answer. So I think the central party is probably the main part, the looking into what the central party is doing. And again, if you look at what the central party is doing, you won't see any of the data in plain text. So you still won't be revealing any information, but you'll get how much noise was added, which should give you, basically an idea of what the actual privacy guarantee is. And then you should also be able to figure out how many parties participated. And so the calculation of how much noise to add is related to how many parties there are. And then there's a couple other components that relate to this. So one of them is, potentially how many queries a single party can do, which, at the beginning might not be known, right? So once you kind of reach your limit, so to speak, then you can't necessarily query tons anymore until sort of other parties have trained their models further, or potentially we would need to add more noise. And so the other part of it would be what sort of differential privacy guarantee you would want to provide. So I don't know how familiar people are with sort of the language of differential privacy, but there's the epsilon delta sort of conceptualization of differential privacy, which I think, as you've said, so there have been sort of failures of differential privacy in the sense that I think the main thing is that both the epsilon and delta that sort of parameterize differential privacy aren't necessarily intuitive. So in practice, people use epsilon basically greater than 8 or 10 sometimes, but most theoreticians would say epsilon is not useful if it's above 1, which is really hard to achieve good sort of privacy because the noise that you add is inversely related to the epsilon. So as epsilon gets smaller and smaller, the noise that you add grows, and you potentially end up with kind of something useless potentially. And so to sort of be, let's say, an auditor who's looking at whether the privacy accounting is done well in the context of CaPC, you would need to know, the number of parties and then how much noise is being added in the sort of central party or the content service provider. And that hopefully would not give away any information to the auditor about the sort of party's data, because all you need to know is that noise component. And then sort of, I think though that what you would need is sort of noise over time. So the noise is drawn from, for example, a Gaussian or a Laplacian distribution. So you would need a lot of noise to know whether or not that noise is actually being generated from the proper distribution. And then you could, perform something like Kolmogorov, like Smirnov test or something like that, just to test whether or not that those sort of generated noise is actually coming from the correct distribution. So I think that answers your second question, but in the process of that, I forgot what your first question is. I'm so sorry.
Actually, you answered both.
Okay.
Yeah. So, I mean, do you think, and I'm thinking a little bit of like Mulligan's paper, Expose Your Epsilons, and some of the issues there have been with, really being able to assess when a company or an entity says they're providing privacy, like, yeah,
Right.
what is their epsilon? What privacy in terms of the noise being added are they actually providing? So I was kind of, it sounds like within this model, it would, providing information about, like the degradation and like the delta epsilon would provide sufficient information.
So I think it would have the same pitfalls as just like differential privacy, where you know what noise is being added, but you don't necessarily know, like you can like theoretically know what the underlying distribution is. So like, let's say the epsilon, the delta, how many queries all of the parties have, how many parties are collaborating on each step. You should be able to calculate what the distribution is that the centralized party should be drawing from. But as I said, you would need a lot of points that show you what the noise was to determine whether or not the central party was actually drawing from that distribution. And I'm guessing that's generally what the sort of problems are with DP sort of in general, is like, even if you know the noise, and there are like reasonable tests, like I said, like the Kolmogorov-Smirnov tests, like in statistics and stuff, that if you have a bunch of points, you can determine whether or not they've been drawn from some distribution. But those have, they're probabilistically going to be correct or not correct. So there still is, a chance that they might not be correct. And sort of that probability that they're sort of not correct goes down as you have more and more points that you're actually measuring. But, if you only have a few, then it's pretty unlikely that you'll be able to say something meaningful about whether that noise was drawn from the correct distribution. Hopefully that answered your question and didn't like confuse you more. Yeah, sorry.
It totally does. Thank you.
Okay.
I appreciate it.
Yeah.
Well, then I'm going to come in now with a pretty, like, I guess, more general question. I think that, for folks, even though I know people don't like to speculate, but I think, if you could hold a carrot up in front of people's faces and we're like, hey, this is where we could be going to in like 5 years or so, what kind of potential applications could be useful here? I mean, like there are potentially so many. And how do you in particular see, that field progressing, and especially in like light of recent AI, progress?
Yeah, so personally, a lot of my research has been on like healthcare and AI applications to healthcare. So I think I'm more motivated towards sort of that application scenario. I think there's, a lot of potential for collaboration between parties, and especially there's been a couple recent papers that have shown that standard differential privacy methods in the context of healthcare, which is really one of the main like motivators for differential privacy, it actually works quite poorly in most healthcare scenarios. And so, one sort of idea that some people have, and there's kind of debate about this, is that, if you have a lot more data, hopefully that would sort of solve the problem to some extent. And so potentially like hospital collaboration could be one thing. And aggregation, there's like a lot of deployment issues with that. Like aggregating electronic health records from different hospitals is like very difficult. But I think that's sort of like the main sort of scenario that I hope for, especially just doing research in sort of machine learning for healthcare. And also because there's sort of some other things, like I was saying, like right now, federated learning works really well with like millions of parties. But with like, let's say 6 parties or something, which is, quite realistic. Let's say like a town or like a city wants like all of their hospitals to sort of potentially collaborate. That necessarily isn't that many, might be like 6 or something. But they all do have a lot of data, and we would want that, in the end, they would get some benefit from sort of collaborating. And so those are kind of the current sort of scenarios that I hope to see improve, especially even not in the federated setting. Like I hope that we can sort of make differential privacy work well in the context of healthcare. And because that was sort of one of, I would say, the motivating sort of applications for differential privacy. So yeah, I think that was one thing I would say.
Totally agree. We also have the biotech and longevity group, and it's a big deal.
Yeah, yeah.
Space too. And so I think any solutions would be would be very welcome in that space. And lastly, we had Georgios Cases, who was at Open Mind before as well, and he also focused on privacy preserving machine learning for healthcare. Maybe I'll drop a link to his work here in the chat. Okay, we have kind of a question.
Hi, thank you so much, Natalie, for the talk. Just a very quick one. I know we're running low on time. On the verifiable computation part of machine learning, the citation you cited just one. So I was wondering if there's a big difference between the verifiable computation from the standpoint of learning and the verifiable computation from standpoint of you have the model. I want to query something from you, so you have to prove that you did the computation correctly. Is there a big gap between those two subfields? Thank you.
Yeah, that's a good sort of point. So I think and I have to say this is not like necessarily my like expertise on sort of verified computations. I know that there's a long history of verified computations in sort of cryptography in general, and like I think they're quite robust. I think one of the things that might be difficult potentially in applying sort of verified computations, and I don't have like a lot of ideas on how you would do this necessarily. Like I think that let's say in the scenario where I give someone data and I say, can you perform a gradient update on this data? That's maybe easier to verify. But sort of in the context where, let's say that I know that you have some data and I'm asking you to perform a gradient update on that data. Even if you perform the gradient update correctly, but let's say that you just randomly generate some data to feed through the model, it's hard for me to verify whether or not that data that you put into the model was actually real data or not, which I think maybe falls slightly outside of the verified computation setting, but it's still sort of an issue with this sort of corrupted computations. I can still, like, let's say, perform the computation correctly, but if the data is, just random noise that I made up, then it might still not be that useful. So I think in the setting where you're like giving data to someone and then they're, computing something and returning it to you, that seems more straightforward to me in terms of sort of the jump from traditional verified computation to sort of verified computation in learning. The sort of jump to like, well, the data could be anything, it's hard for me to make, and I'm not sure. I don't have an idea of what the solution at this point would be to that.
We're at time now, and I do want to let you go on time, but I don't want to let you go before the final question, which is, if people are now very excited about your work, what couldn't they do to help your work in particular, the work of your institution along, like very concretely, very focused on your individual bit?
That's a very good question. So I guess like the field in general, I think definitely like differential privacy would benefit from a lot more minds. Like it feels very nascent, even though it's been around actually for like almost 10 years now, which is kind of crazy. But I think like kind of putting more towards that. And I think especially putting more towards sort of privacy fairness trade-offs. This is like a huge issue right now that I think a lot of people are working on privacy utility trade-offs, but privacy fairness, like most settings that require high privacy also require, some mitigation of bias. So I think that's what I would say. And also thank you so much for hosting me. And if anyone wants to reach out, I have a website, and I can also put my sort of contact information in the chat if that would be helpful.
Wow, thank you. This was really, really, really great. I also received a lot of private messages just like, this was awesome. I'm going to rewatch this later. So thanks a lot for coming on. And I hope it wasn't the last time that we had you on. And I'll be in touch with the video, which will be on YouTube soon. But thank you so much for joining, everyone. Have a wonderful rest of your day, guys.
Yeah, awesome. Thank you so much. Bye.